And go ahead and start. So last week during the Thursday meeting, everyone hopefully got a CEA that's all finished or at least close to being finished. That we can start post-processing to get some actual sizes and
Yeah, I don't.
what was that? I get some actual dimensions and sizes and flow rates and stuff on your engines. So now, yeah, we're going to cover how to use that data to post-process. Let's see. Can everyone hear me except for Carrie, I guess? Yeah. Okay.
Thank you.
Hopefully, I shall get that fixed. Can you hear us now, Carrie? Okay.
I'm just jumping. You have one? Oh yeah, now I have one. It'll be an hour though. I'm just doing a bunch of calculations.
Okay.
Let's do this.
So CEA gives us a bunch of stuff that we can use, like the exit Mach number and the speed of sound at the exit, the throat density of the flow and velocity, and then the area ratio between the throat and exit areas. And with that information, we can calculate a bunch of other stuff, like the mass flow rates of the propellants that we need, the nozzle throat area and radius, and then the nozzle exit and nozzle inlet area and radius as well. And then some other properties that we find from Google that will be able to help us find the length of the combustion chamber to get final dimensions on everything about the nozzle and combustion chamber for your rocket engines. So first thing we're going to calculate is the mass flow rates. And this basically comes from the principle of momentum. I don't know if you guys remember in the first lecture we gave, we talked about basically the way a rocket engine generates thrust is you throw a bunch of mass of combustion gases out the engine at high velocity, and that creates thrust. So just a short derivation of kind of how that happens. So if you remember, momentum is signified by P for some reason, is mass times velocity. And then a change in momentum, also known as impulse, is mass times delta V, change in velocity. And also from the definition of an impulse, total impulse is equal to force on an object times the time that that force is acting on the object. I'm not sure if that was covered in physics. This might be something more from dynamics, but yeah, that's the definition of an impulse. It comes from both momentum, change in momentum, and from force times the time acting on the object. So from that, using this definition for impulse, you have F time, force times time equals mass times change in velocity. And if you go ahead and divide both sides by time, you have a force equals. And then if you have amount of mass over time, if we assume that you have a consistent flow of mass, like we are going to have in the engine, you can say this is basically just a mass flow rate, which we denote that by just using m dot. The dot just signifies its rate of mass flow per time. And then velocity, or change in velocity, is from basically how much you change the velocity of the combustion gases. So we start with our propellants in the propellant tank, right? So they're at a velocity of 0. And the final velocity is your nozzle exit velocity. So for this, you have velocity at nozzle exit minus velocity initial, which is 0. So this just becomes exit velocity. So from there, that's where you get this equation. You have force, your total thrust in newtons, equals total mass flow rate of your propellants, which you can assume, since conservation of mass, the total amount of fuel and oxidizer you flow into the engine is going to equal the same amount of mass that flows out as combustion gases. A lot of heat and energy gets released, but the amount of mass in that stays the same. And then, so that mass flow rate times your exit velocity gives you thrust. And all the units for this is force is in newtons, mass flow rate is in kilograms per second, and velocity is in meters per second. Yeah, I would recommend doing all of this math in the metric system, because the imperial system is a big headache. Lots of unit conversions that need to happen there. So now, so we start back from this equation. So thrust force is a parameter we picked a few weeks ago. So you have this. Exit velocity you can get from CEA, and then we use those to calculate the total mass flow of propellants. So first, how do you get the exit velocity? Let me, if I can exit. PowerPoint and go to, so this is the CEA for the example engine that Arun and I did over the summer. So what you have that's useful to us is Mach number at the nozzle exit and the sonic velocity at the nozzle exit. So basically Mach number, so Mach number is a quote unquote non-dimensional number. It has no units. It's essentially the ratio of the flow velocity to the sonic velocity, or we use A to define it as acoustic velocity. They're the same thing. It's the speed of sound through your fluid, which is a function of the fluid, its properties of the fluid itself and the fluid temperature. You don't need to know this per se, but just as a reference, acoustic velocity equals a very badly drawn square root of KRT. K is just a property of the gas. R is the specific gas constant, and temperature, or T is temperature. So this is a function of temperature. That's why it changes at different points in the nozzle. But regardless.
For reference, at normal room temperature in air, sonic velocity is 343 meters per second. So you can see here that because of the elevated temperature, we're about 3 times that.
Yeah. Yeah, very, very, very fast. So basically now with this definition, we can get the exit velocity with those two. So if we take the sonic velocity at the exit and just multiply it by the Mach number, that will get you your exit velocity in meters per second. I don't have my calculator on me right now, but roughly 1,000 times 3.7 gives you 3,700 meters per second ish. Oh, actually, Arun and I were looking at this earlier, and for some reason, ISP, this is literally just the exhaust velocity. Yeah, I don't know. It's weird, but yeah, so this times this equals 3,500-ish.
That's usually not what specific impulse means, but this is how the CEA calculator is defining it. But really all that means is the exhaust velocity, or the velocity at that point.
Yeah, I don't know why CEA is outputting that as ISP, but
the numerator in the Mach number equation is literally just velocity. So to the Mach number is just how many times the speed of sound you're going.
Yeah.
That's the local speed of sound.
We have a chat question. Oh yeah, that's what everyone was just answering. Let's see. Back to the presentation. Yeah, so now we have exit velocity. Where did my... yeah, so now we just got exit velocity, just Mach number times the exit acoustic velocity. We have the thrust that you picked. So then literally just F over exit velocity equals a very badly drawn m dot total. Yeah, so this is the overall flow rate of both combined oxidizer and fuel. So in order to find the flow rates of each, you have to do a little bit of math that is actually kind of confusing. So because you have the OF, so you use the OF ratio, oxidizer to fuel ratio. So that's we picked that, iteratively last week using CEA. And this is the ratio of mass flow of oxidizer to the mass flow of fuel, in mass. So if I go back to the CEA, cool. Let's see what our OF ratio is 1.6. Erase this. Can I not scroll while I have the pen open? Okay, I can't. So basically, if you have an OF ratio of 1.6, that's 1.6 over 1, which means for every 1.6 kilograms of oxygen or oxidizer, you have 1 kilogram of fuel, which means in total you have 2.6 kilograms of mass, or kilograms per second mass flow total, which is equal to your OF ratio plus 1. So then in order to find the mass flow of oxidizer, basically, since it's ratio over fuel, you take your OF ratio divided by that sum of essentially the mass total. So OF plus 1, and then multiply it by m dot total. And that gives you your mass flow rate of oxidizer. Yeah, pretend I finished writing that word. Yeah, that can be kind of confusing. So does everyone understand why it's this formula? Is everyone good with this? Okay, cool. And then once you have your mass flow of oxidizer, getting the fuel is really easy. It's, m dot total is m dot total. So you just subtract m dot oxidizer, and now you have your mass flow of fuel. Nice and simple, just like that. So yeah, that is how you get your mass flow rates of your propellants from the thrust and CEA outputs. Are there any questions on how we got there? I'm also going to go through the spreadsheet of the example engine and kind of show that math again. All right, cool. If there's no questions, we shall move on to calculating dimensions of stuff. So has everyone seen this formula in physics, or if anyone's taken fluids? Basically, it's just the continuity equation, mass flow rate equals density of the flow times the cross-sectional area times the flow velocity. Basically, this is just a relation that we use for if you have changing cross-sectional area and whatnot, you can find the velocity and stuff. But it also is very helpful to us here, where we just found the total mass flow rate we have. CEA gives us the density of the flow, and it also gives us the velocity of flow. So we can use this equation to solve for the cross-sectional area. And we're doing this at the throat because that's easiest, since CEA gives us the ratio of throat area to exit area, and because I don't know if you guys remember us all the way back at the beginning, the nozzle chokes flow so that it's at the speed of sound at the nozzle throat. So your Mach number is 1, and the acoustic velocity is just the flow velocity. So I'll go through that on the CEA page. Let's see. So where's Mach number? Yeah, Mach number at the throat, this middle column, is 1. We have the sonic velocity here. So if we we have m dot equals rho a v. We have 1, 2, 3. So your cross-sectional area is m dot total. This is mass flow total that we just solved for, divided by the flow density, which is denoted by rho up here. This is kilograms per cubic meter. Another interesting quirky thing about CEA is that when it does scientific notation, it just kind of puts a number and then leaves a space, and then the power is over here. So this is 9.6 times 10 to the 0. So this is just 9.6 kilograms per meter cube. Over here, it's 6.65 times 10 to the minus 2. But we are interested in density at the throat. So our density is 5.9 times 10 to the 0, so just 5.9 kilograms per meter cube. So that goes down here, and then flow velocity is just this. Well, this times the Mach number, but since the Mach number is 1, we can just use the sonic velocity at the throat. And you do that, and you have your cross-sectional area at the throat.
And yeah, just to reiterate, the Mach number at the throat will always be 1 in the type of nozzle that we're working with is a converging, diverging, or deal of all nozzle. That's just kind of how they work. We're not going to get into the physics of why that's the case, because honestly, it took us a couple of years to figure that out. But that you can basically just say that it's always 1. If it's not, your engine's not going to work right, and it will never be greater than 1.
Yeah, it because of physics, it can never be greater than 1, and if it's less than 1, you just have a flamethrower, and that's fun but not useful to us. Yeah, so once you've found your throat area, it's really easy to find. Whoops, that is not the eraser. It's really easy to find your exit and inlet areas. Oh, also, I just realized we're talking about inlet, throat, exit, all of this stuff. Basically, if you have your rocket engine, and here's the combustion chamber, and this is just kind of a cross section of it. Nozzle inlet obviously is at the inlet. Nozzle throat is at the narrowest point of the nozzle, and then yeah, nozzle exit is the exit. Just make sure I wasn't confusing anyone if nozzle throat is technical jargon. But anyway, so that was what we just found was the area at the throat of the nozzle. And CEA has made it very easy for us to calculate the exit area because it gives us that ratio. So this is exit area divided by throat area at that ratio. This is actually very much dependent on the pressure ratio that we set at the beginning that we put into CEA. That pretty much informs us how big we need to expand the nozzle. But anyway, yeah, this is literally just a ratio. So if you have exit area over throat area is 31.7, you just multiply that by your throat area and those cancel. And now you have your exit area. Simple as that. And now, so inlet area is fairly straightforward, but I think a few people over the summer were a little bit confused by this. So there is no like set way to calculate the inlet area. There's I just know from my research I found there's a general rule of thumb that your inlet area equals 4 or more times the area of the throat. I guess for the purposes of this, just use 4 times the throat area, unless you get a very long and skinny chamber, in which case you can go greater than that just to make it more aesthetically pleasing. But the rule of thumb behind that is basically you need at least 4 times the area at the nozzle inlet than the throat in order to get choked flow, where it reaches a Mach number of 1 at the throat. And also, I don't remember. I don't know if you guys remember, but during the CEA lecture, someone pointed out that CEA was assuming an infinite area combustor, and basically, when that happens, the infinite area assumption is basically that in your combustion chamber, the flow of combustion products is so small compared to the flow at the nozzle throat and exit that you can basically just assume that it's 0. And in order for that assumption to hold up, the cross-sectional area of the combustion chamber and the nozzle inlet area should be at least 4 times the throat area. Because, m dot equals rho AV that we were just talking about. Increase the cross-sectional area, you decrease the velocity in that section. So that's pretty much why this is the way that it is. Yeah, don't think into it too much. And then obviously once you have all of your areas, area of a circle formula, um, to get your radius, diameter, whatever it is that you're going to put into the CAD. So that is that. Dimensions for the nozzle. Are there any questions on that? Actually, before I continue, for the actual shape of the nozzle, that is a very poorly drawn nozzle, but hopefully you get the idea. So we've figured out the radius of each of these sections, but now, what's the geometry in between? I think it's rule of thumb for a very simplified conical or cone nozzle is to use half angles. I think it's 15 degrees,
Yes, degrees.
On the exit side and 30 degrees on the inlet side. Is that right, Arun?
Yeah.
Yeah. And then just kind of smooth out the throat. We are going to do some fancier stuff and make the exit a parabola, but that is a lesson for next week, I think.
Yeah, that should be next week.
Yeah. So next week you'll figure out how to make this fancier and improve the efficiency beyond just a simple cone. But
It's fine to have the inlet be a cone.
The cone will define basically your length.
Right, but I'm saying you're saying that you'll make the exit a cone or the exit a parabola. Will we leave the inlet still a straight line?
The inlet, so sorry, Arun, for kind of talking over you, but I don't think I've found any math that says the optimal geometry of the inlet nozzle. I just know for regen we kind of smoothed this out into two tangent arcs, just tangent circular arcs. I really don't know what the optimal inlet geometry is.
Technically, it's a LV hack curve, but no one uses that because you're talking about hundredths of a percentage change. Really, the converging section of the nozzle, the geometry matters very little. There are some solid rocket engines and even some liquid engines that are used in compact missiles that they don't even have a curve. They literally just have a wall that goes down to the throat. So point being, we'll probably all just use the double circular segment that Jackson's kind of sketched out there for the converging section.
Yeah.
Cool, thanks.
Yeah. So now that I talked about the half angles and stuff for the cone, are there any more questions about nozzle geometry stuff? All right. So now we'll move on to the combustion chamber, which I think proved to be the most confusing part to people over the summer. So hopefully I will explain this more clearly. So basically, in order to find the length of the combustion chamber, we use something called the characteristic chamber length, or it's written as Lstar, also called Lstar. Basically, this is a parameter specific to the propellant combination you're using, and it's basically a weird measure of combustion reaction rate. I don't think I'm going to go into the exact definition of this since that seemed to confuse people over the summer, but basically it's just a way for us, a standardized way for us to tell us how big of a combustion chamber we need. And we use Lstar times the throat area to find the required velocity or volume of the combustion chamber, sorry. And this works out because remember back to m dot equals rho AV, as the cross-sectional area of your combustion chamber increases, the speed or the velocity of the combustion products goes down. So you have a longer time in the chamber for it to combust, and you need a shorter chamber. So it's related to the volume of the combustion chamber, and Lstar is just the way it's defined is related to the throat of the nozzle, because that's kind of a standard point since that's where you're choking the flow to Mach 1. Yeah, hopefully that made sense. Lstar is not something that CEA will give you. It's something you're gonna have to do some Googling for. Otherwise, I think Arun said if you don't find one for your propellant combination, use an Lstar of 2 meters.
Yeah, it's for reference. The for like let's say liquid oxygen and kerosene, which is the one that the Regen engine uses and a pretty common one, it's 1.3 meters. Unless you're using something really weird and kind of bad, it'll be under 2 meters. You don't really lose much by having extra length. Like, don't make it absurdly long just because that's weird, harder to build, and also heavier. But it doesn't matter a ton. Yeah. So, for example, for this example engine that me and Jackson did, we used really weird propellants, and so you can see it's closer to 3 meters.
Yeah, ethanol burns very slowly. I also realized looking at this CEA, we actually did the weight percents out so that our fuel is a mixture of ethanol and water in the same ratio as Everclear because we were just beaming. And yeah, it's very slow at combusting. We found out. But yeah, most of the common fuels you'll be able to find some like NASA paper if you Google characteristic length, or if you just Google like literally Lstar like this for let's say kerosene box, you'll probably find something. And yeah, if you don't find anything for a weird propellant combination, just use 2 meters. That would be a safe assumption.
Yeah.
And we can always revisit that if we're actually going to build.
No, Lstar is not C-Star. C-Star is basically an idealized, if everything was perfect, what would your exhaust velocity be? It's a way of measuring the efficiency of your propellant combination, even if ignoring like what your chosen pressure or any of the other parameters. Lstar is just a way to, basically, there was a bunch of very sad grad students at a national lab like 40 years ago that did a ton of testing to figure out how long different propellant combinations took to react. And that's where the Lstar comes from, because all it actually is what would the length of the chamber need to be to get everything to combust completely if the chamber's cross-sectional area was the same as the throat cross-sectional area. We don't actually want to design our engine with like that because of the reasons Jackson talked about before, but it's just a good way of measuring how much chamber volume do you need, basically.
So yeah, basically, if I can figure out how to, okay. So yeah, you find your Lstar on Google. You have the throat area, which we just calculated, and now we have the required chamber volume. And some textbooks like RPE or the how to build test or design build test liquid rockets tell you to include the nozzle inlet area in the chamber volume. I say you don't really have to, because as Arun said, if you make the chamber bigger than required, nothing bad happens. Like the combustion reaction goes to completion, and you might lose a little bit of efficiency, and it's a little bit heavier than it needs to be, but it's not as bad as making your chamber too small and not completing the reaction as you're going through the nozzle. So I don't include the nozzle inlet area in the chamber volume calcs because that's more math that I don't want to do. I just literally say that since you have chamber volume equals Lstar times throat area, you can find the length of your chamber just by taking that and dividing it by the inlet area you selected or you found in the last step. And then again, as you see, the chamber length depends on the inlet area. You have, that's where I said start with 4 times the throat area for the inlet area. And then if you get a chamber length that's like stupidly long and this is not very wide, you can increase area until your chamber dimensions are more aesthetically pleasing. That's what happened over the summer with the engine we were doing. The 2.7 Lstar is massive, and that made the chamber very long and skinny, and we didn't like that, so we beefed it up and made it like, yeah.
I think we ended up using something like 8.
Yeah, actually, what did we end up using?
Yeah, actually, we might as well go through the spreadsheet version of this.
Yeah, that's what that was the end of the maths for this week. And now we can go through the spreadsheet. What did we end up using? Where's inlet? Oh no, we did use 4. I think we just sucked it up. I know Marisol and Dom's group, I think you guys used something larger, right, Marisol?
I honestly don't remember.
A 1/4 of a meter. Yes. That's probably expected. It depends on what your inlet.
Absurdly oversized, so
yeah,
you're not going to see numbers this scale.
Yeah, our engine is definitely not on the. This example is not on the same scale that you guys are going to see. It, yeah, a 1/4 of a meter should be about right. I think. For IPA GOX, I want to say the chamber diameter ended up being something like 1.5 inches, and the throat diameter was probably like between 1/4 and 1/2 inch, and then the exit area was again something like between 1.5 inches and 2 inches. So that was a very small engine. So if we're trying to build something about that scale, then yeah, a 1/4. Actually, a 1/4 of a meter seems pretty big for that.
That lines up.
A 1/4 of a meter, 250 millimeters to 2.5. Wait, is that 2.5 centimeters, or am I being dumb? Throat radius is about 4 centimeters.
Oh, that seems large.
That is a little bit big, yeah.
We can look at that in a bit, but
The exit radius is 24 centimeters.
Actually,
yeah,
with the low pressure
that
ratio,
is a bit big.
Well, with the low pressure ratio, that could be real because that exit radius makes sense.
Okay.
Depending on what pressure you chose to design for.
Oh boy, it's almost 9 o'clock. Let's get going with this Example calc. So again, I highly recommend doing all your math in Excel. I do this for like everything I do now. Like sometimes I'll even do my homework in Excel, if it's an equation I'm going to be using a lot. But yeah, so here's where we took all the CEA values that we were looking at before from this, and we put all the relevant ones in here. So that would be your exit Mach number, exit sonic velocity, your area ratio, throat density, and throat velocity. Yeah, so those are all just numbers, no fancy equations there. And then here we have all of the calculated values. So I'm just going to go through and try to calculate these again, just so you can see. So exit velocity is exit sonic velocity times exit Mach number. Yeah, 3,468 meters per second. And then you get your mass flow of propellants total equals, what did I say? F over V. So our thrust divided by the exit velocity we just calculated, 128 kilograms per second. Oh boy, we did fuel first, but I'm going to do oxidizer first since that's what I showed you guys today. So that would be your OF ratio divided by OF ratio plus 1, and then times this mass flow total equals, yep, 78.95, still accurate. And then this is just this guy minus that guy. Okay, you're just doing that for everyone to take a look at. 49.3, yep, that matches. So yeah, you can calculate either first. We just showed you guys oxidizer. The formula for fuel is here. It's just 1 over OF plus 1 times that. Let's see. Yep, so now we found both of the mass flows of oxidizers. So now for the all the nozzle dimensions. So throat area would be mass flow total divided by the density of flow at the throat, which is right here, and also divided by the throat velocity, which is right here. And so there we got an area of 0.017 meters squared. So then to find radius, just take this and times the square root of the area divided by pi. Funny, that doesn't match. I made a typo. Where did that come from? So that should be E20, and that shouldn't be there. Yep. And then exit area, take this guy, or oops, throat area, and times it by the area ratio. God damn it. Multiply it times the area ratio, and then yeah, you can solve for the radius, and then inlet area 4 times throat gives you that, and then again area formula to get radius. Characteristic length came from Google. So then you can find your total chamber volume by doing characteristic length times your throat area all the way up here. And then chamber length is going to be this guy, chamber volume divided by the inlet area. So that's 675 millimeters, which is what, 67 centimeters? About two feet, I think.
Yeah, roughly.
Yeah. Oh. I see. Yeah, we did. Yeah, we didn't use the inlet radius here. We made it bigger. We just picked a random number that was greater than this one. And the actual chamber length we used was what is this, 37 and just over a foot. Yeah, so there's all of that. Yeah, sorry I had to rush through that because we're kind of running out of time. But for the last 5 minutes, does anyone have any questions? Want me to show another formula again? We'll send you guys the link for this spreadsheet to look through as an example.
And we'll also have this recording up because this is one of the weirder ones I want to review.
So yeah, questions on any of what we did today? So the inlet area, we actually did it 2 ways in this spreadsheet. The first way is just 4 times the throat area. Since again, that's just generally the rule of thumb I've seen in most textbooks on how to make sure your combustion assumptions are still valid. We kind of just pulled this out of thin air. As long as it's greater than the so that this is a radius, yeah. So as long as it's greater than this radius that you got from the 4 times the throat area, you'll be fine. We just picked a bigger one to make it look nicer.
The one note on that is just make sure that your radius, or your radius is not longer than your chamber length. Because then
yes, that is another good. Yeah, you want it to be more of a cylinder than a pancake, but you can do anything.
You can get them pretty close to equal.
Yeah. I think technically the most efficient combustion chamber is a sphere. Volume of the chamber.
So you have the volume of the chamber just given by your Lstar times your throat area, because Lstar is defined as the volume that the chamber needs to have so that you have enough like residence time in the chamber for the combustion to finish. So yeah, it's just that's how you get the volume from Lstar. If there's not any other questions right now, so we were considering going through the simple SolidWorks for this, but obviously we were out of time. If you want to and know how to use SolidWorks already, feel free to make the engine with just like a simple revolved body using our completely arbitrary wall thickness or whatever you want to do. And that way you can just kind of have something to look at. If not, depending on how Thursday's time goes, maybe we can start getting people into that. But next week is when we'll really start doing the geometry for the CAD. If anyone does not have access to SolidWorks because they're not COE, we'll put the links for how to get that in the Discord. Well, actually, we'll put it in the links for COE in the Discord. You need to request it if you are not COE, and I don't know how many licenses there are left, so hopefully at least one person in each group has access to that. If you don't know how to SolidWorks at all, don't worry about it. This intro track doesn't need super complicated SolidWorks, and also, well, it shouldn't take more than like 20 minutes to learn the simple part of this.
All right. If no more questions, thank you guys for coming, and have a good rest of your night, and good luck on midterms.
Thank you.
Thank you.
Very much.
Thanks.
Thank you.